as we jump into this last one, you'll probably notice there's a lot here that's kind of all at once and thrown at you. If something's super important, we're practicing it over and over in class. So don't worry, this is our first attempt and our first look at it. On part A, after looking at our previous reactions, net ionics, and balancing, hopefully this was something that kind of stuck out and was a reaction you felt comfortable with. Silver nitrate and sodium sulfide, we write and balance those based upon their charges and do a double replacement. And then we think about what is aqueous and what is solid. I didn't put any states of matter in here because they are not required when you write a reaction unless I tell you to specifically, or we haven't seen it, but unless the AP exam specifically says to write the state itself. Once again, that hasn't happened. But what we do have to do is kind of analyze our products. We know the left side are solutions, but what about the right? Well, both sodium and nitrate are in our rules of always soluble, but it tells us it's a precipitation reaction. That means if this is soluble, that has to be insoluble. So that's how we can know Ag2S is the product that we have to worry about, and that it's the Ag and the S2 combining for that. And you might write out your molecular, you might even write out a complete ionic. But once you get enough practice on this, you would see, well, nitrate can't be it. Sodium can't be it. So it has to be silver combining with sulfide to make this. So we've seen this a few times, and we're going to keep practicing and repeating that. Part B is about Bronsted-Lowry acid base. This may have been introduced a little bit in first year chemistry. It may not have been. It will be a huge focus later. But if we don't refresh ourselves a little bit now and build our skills, then we're going to be playing catch up. So we want to think about what are the definitions of acids, bases, conjugate acids, and conjugate bases. The acid is the thing that gives away the hydrogen. We notice that HBr has a hydrogen. It goes to Br minus. It no longer has it. NH4 gains it as it goes from, NH3 to NH4 plus. Note that not only are we exchanging a hydrogen atom, but it is an ion. Our acid turns into its conjugate base. Our base turns into its conjugate acid. And we can kind of recognize once we know either what our acid is, we can prove what our base is, or vice versa. Once we know what our conjugate acid is, we can know what our conjugate base is. Although this is written as a one-way reaction, we'll see a lot of acid-base reactions are actually reversible and in an equilibrium when we get to that topic. So that's kind of why we think of these still as acids and bases. If I go back the other way, the NH4 gives it back away while the Br takes it back in. Here, both of our things start with H, so we're really looking at how they change. Well, this has 3 and it goes to 2, so by definition, acid with conjugate base, and this has 2 and goes to 3, base and conjugate acid. H3PO4 is phosphoric acid. We can call this a triprotic acid. 3 hydrogens. An important piece there is, even though it's got 3 hydrogens, it still reacts by giving just 1 away at a time. And that has to do with lots of things we'll get into, including strength, dissociation, and how the Bronsted-Lowry process works. Here we have a similar situation with 2 things starting with H's, but we recognize HCl hopefully as an acid. HCO3 minus is the bicarbonate ion, and in this case, it gets another hydrogen. So we've got acids and conjugate bases in similar ways for similar reasons. Assigning oxidation numbers is hopefully something that made sense and something that's going to come somewhat easily and naturally. It is related to the charges that we learned on the periodic table when we were just starting off. Hydrogen is +1 in all the examples that we see. When oxygen is a part of a compound, we'll see here, 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 and here, it's a -2. Only when an element is by itself is it a 0. Fluorine is -1. Nitrogen in this case is -3. But what we're thinking about is acknowledging that I've got 2 +1s, 3 -2s, So what does carbon have to be to balance that out so that all of those add up to 0? Well, +2, -6, the +4 balances that out. When I come down to NaClO3, the O is going to be a -2 for sure. The Na, because of its column, is likely and almost always going to be +1. We would normally think of chlorine as a -1, but when I have +1 and 3 -2s for a -6, that means that in this case, chlorine has an oxidation state of +5. We can also kind of look at that in terms of the compound. And oxidation states relates to how much oxygen it's bonded to. Well, it's bonded to a different amount of oxygen in this compound than it might be in another, and that's why that +5 is important. It is not the same as if it was just NaCl in terms of its charge and sharing of electrons. I've got 4 +1s, 1 -1, and then in this case, the nitrogen is the charge that we might predict, a -3. Over here, I've got my magnesium nitrate, my oxygen's -2, my magnesium's +2. But as I look at a polyatomic ion, especially in parentheses, it gets a little bit tricky. I have 3 times 2 or 6 oxygens. 6 oxygens accounts for a total charge of -12. -12 with the magnesium is only balanced out by +2. So that means the nitrogen has to account for the rest of the positive, or for +10. But oxidation numbers are assigned per atom. There are, based upon our subscript out here, 2 nitrogens. So each nitrogen is a +5. In this one right here, we kind of have to figure out what's going on. Copper has a few different charges and oxidation states. So in this case, we need to kind of remember or know that sulfate as a whole is -2. SO4 is -2, and therefore the copper is likely to be +2. A +2, 4 -2s leaves us with sulfur in an oxidation state, or in a situation this time, rather than being a sulfur by itself or a sulfide that might be a -2, it's more oxidized, a higher oxidation state. And then the oxygen is by itself. I'm going to cut this off here and have one more video for these because these are a little bit longer and more intense.